Thank you, Sarah. Thank you for inviting me today. It's interesting. I've been here for just a year, enjoyed my time here quite a lot. And today, the other day when I got this email about giving a talk, so normally when I'm out there giving a talk, most of it is the research that I do, so a bunch of equation, and 10% of it is what it means to the general audience. And so this was going to be flip. So it was interesting while I was trying to think about what to say. And I would like to thank you for inviting me because it gave me the opportunity to think about what it means, what I do, what is the relevance of it in the broader realm of things. So overall, my area of expertise is in the domain of water. I'm interested in different kinds of water issues around the world. So just to give you an idea, sanitation and access to clean water, maintaining aquatic ecosystem services, floods, food, water pollution. So I teach a water resource sustainability class this semester. It's a graduate level class where we talk of water issues around the world. My particular expertise is in the domain of water quality, water pollution. So basically to figure out how water flows over the landscape. And when it flows over the landscape, you have humans contributing different kinds of waste to the water. What is the chemistry of the processes happening within the water and what it contributes to downstream, as in Gulf of Mexico hypoxia and things like that. So I'll explain my title at the end. For now, let me say that my interest right now here is to look at water quality in the Mississippi Basin. The Mississippi Basin drains about 41% of the US, so that the colored area over here is the Mississippi Basin. And one of the big issues of the Mississippi Basin is that it has contributed to hypoxia in the Gulf of Mexico. Hypoxia is not unique to the Mississippi Basin. If you look at all the red dots in this figure, all of these are hypoxic regions around the world. So look how the east coast of US is. Look at Europe. So hypoxia is a pretty serious problem. And hypoxia, by definition, is a condition when oxygen concentrations in the water is less than 2 milligrams per liter. And so this is the number of hypoxic sites in the world. So hypoxia in 1900s was very, very low. And look at the rate of increase in hypoxic sites around the world. So this is a pretty serious problem and increasing at a very, very fast rate. So what contributes to hypoxia? Well, we do. So this is an interesting figure. I apologize for the poor quality of it. This is what I got. So the black dots are still the hypoxic regions around the world. And green indicates that there is low human footprint, low population density. And the redder the areas go, there is more population density. So you see how population density correlates with hypoxic regions? So it is all a part of humans changing the ecosystem. So what is hypoxia? What does hypoxia do to the system? Well, that is captured very well by this one sentence, right? It's breathing of the ecosystem. So a little bit more. So when you have hypoxia, when you have low oxygen concentrations, your benthic organisms die because they can't move away. So benthic organisms are those that live at the bottom of the ocean or the lake. So they die. The fish, sometimes they die. Sometimes if they can migrate away, they migrate away. Their food resource is taken up, so they migrate away or die. Effect on humans? Well, fisheries are affected, tourism is affected. So this a lot of you might be familiar with it, but I'll just go over it briefly. What causes hypoxia? So here you have fresh river water that brings in a lot of nutrients. And because this water is fresh water as opposed to the salt water of the ocean, it floats on top of the seawater. Plus, this water is also warmer. So you have these two layers, the top layer which is lighter, warmer river water, and the bottom layer which is denser, saltier seawater. Now, when this fresh water brings in a lot of nutrients, what it simulates is a lot of growth of phytoplankton in this top layer. The phytoplankton then die and they sink to the bottom of the ocean. When they sink to the bottom of the ocean, there's decomposers which decompose this phytoplankton, and in the process they consume a lot of oxygen, which creates this anoxic or hypoxic zones in the bottom of the ocean. When you have hypoxia, some of the fish live, whereas the bottom of the ocean, the benthic organisms die. So what causes hypoxia? Large amounts of nitrogen loads to the Gulf causes hypoxia. So I found this interesting. I was reading this article the other day about an Iowa farmer talking about the fact that less than 4 decades ago, when he remembers his father growing corn and fertilizers first coming into play in a very, very strong way, how fast the corn grew and what a big deal it was. And we can trace back that story to the 1900s when first ammonia was synthesized by the Haber-Bosch process. What that brought in was this huge green revolution, large increase in agricultural lands all over the earth, and world hunger was reduced to a large extent. So that is the benefit of synthesis of fertilizer. What came as a repercussion is hypoxia. So what you see over here on the x-axis is 1900 to 2000. And on the y-axis you see mass of nitrogen, right? So if you look here, if you look at this line in here, this is industrially fixed nitrogen that is added to the system. And the red line here is the number of hypoxic sites. So you see how these two are correlated. So increase in nitrogen in the world resulted directly to increase in the hypoxic sites in the world. So a brief about what happens when fertilizers are applied to the soil. So here, this is fertilizers being applied to the soil. And within the soil, you have this complex set of processes. And I'm not going to go into the details of the processes, but I just wanted to appreciate the fact that it's not simple to go out and figure what happens in each of these stages and the fertilizer that you're applying, which pathway it takes. But it's kind of known that some of it leaches to the surface water, some of it leaches to the groundwater, and some of it leaches to the deep, deep groundwater and travels very long distances. So this is a figure of the Mississippi Basin with the total loads of nitrogen. So here you see this very dark region is which contributes most amount of nitrogen for the Gulf of Mexico hypoxia. And this is the corn soybean belt, right? This is kind of known also that this is the main contributor. And the phosphorus is also kind of similar. The phosphorus pattern is kind of similar. So here, this is a picture of how nitrogen loads. We saw that more on an overall world basis. This is just the Gulf of Mexico. So here you see the hypoxic zone size and how that relates to the nitrate load. So the open circles in that figure is the nitrogen loading in the month of May, and the closed circle, the filled circles there are the size of the hypoxic zone. So you see in years you have large nitrogen loading, you have a large hypoxic zone. So it's very directly correlated. The other thing, notice the months. So it says nitrogen loading in the month of May and hypoxic zone in the month of July. So why is that so? Well, there is a time lag. You have most of the nitrogen that comes off your field comes in May, June. And then the plankton grow and they die. So that cycle robs the ocean of its oxygen. So that is the time lag between these processes. And by September, the hypoxic zone kind of goes away, because what you have is these storms come in and they mix up the water. So then you have oxygen from the atmosphere mixing the bottom layer, so the hypoxia kind of disappears. So this again is a picture of years along the x-axis and area of the hypoxic zone. And you see that it's steadily increasing. Again, you see these cycles. And the reason you see these cycles are these are kind of the natural cycles that you see in the stream flow. So stream flow is not constant from year to year. You have these cycles, and the hypoxic zone cycles kind of follow that pattern. So the red line, the top red line, is more or less an average of the area over these last 10, 20 years. And the red line here is the action plan. So there was a huge amount of work done on Mississippi Basin action plan, figuring out how much do you need the hypoxic zone to be reduced. So this was the set target, 2,000 square miles. And some amount of models that were built and calculations that was done said that fertilizer applications need to be reduced by 50% to achieve that. So before we go further into this, I wanted to talk about this one point, is that this problem, this hypoxia or any water quality problem, it's not purely a science problem, because you can do all the kinds of models that you like, but ultimately it hinges on linking water quality, water quantity to the socioeconomics of the system. Because if you say fertilizer application reduced by 50%, it's not going to be implemented. And so that's what has happened for a lot of time.